welcome back for another video. Today we're going to be talking about polar and vector value functions. We have a lot to talk about with polar functions. We're going to be talking about, for example, how to find the area between two different polar functions. I'm going to be talking about arc length, equations of tangent lines, and then at the end of the video we'll just do a brief introduction into what vector value functions are. So we stopped last video talking about polar functions, and so let's get a picture up just to see what we're talking about today. And so basically what we have is, what looks like our normal Cartesian plane with an x and y axis, but we're going to be viewing points a little bit differently. So what I mean by that is we have what we call this point right here in the center, which we're going to call the pole. And so the pole is just our sense of center in this coordinate system. And so what we have is a series of concentric circles centered at the origin of the pole. So something kind of like this radar map that we have here. And what we're going to have, for example, is maybe a point, let's say right here. And so this point is on the circle, maybe of radius 3. And so in particular, it's also at some angle to the positive x-axis. And so let's say that the angle that I have right here is just alpha. And I have another angle that's going to be a little bit greater than alpha. And then going out to here. And this angle is going to be beta. And so recall, so what we have is a polar function is one where our input is an angle and our output is a radius. That is just a straight line distance between the pole and the point. So a polar function is of the form r equals to f of theta. And so we very clearly see our input here. Input is going to be an angle, and like I already said, our output is going to be the radius. So this is going to be our output. And so some examples of some different types of polar functions. Maybe you'll see something, probably with a lot of cosines or sines, but it could be something simple like r equals 2. This would be a constant polar function. This would just be a circle of radius 2 centered at the pole. Could have something like this, a cosine of 2 theta, or r equals, whatever you want, 1 plus sine of theta. These will all look a little bit different. So let's go back to the graph we have on the left for a moment. And in particular, we're going to look at, just some random curves. So let's say what I have is something like this. So I'm going to erase these a little. One moment, please. Yes, okay, that's good. So what I have right here, what I've drawn, this is going to be some function f of theta, right? And let's say I want to find the area right here, the area that I'm shading in black. And so what we're going to do is, we know that we start collecting area, we start looking at this area at this angle right here, alpha equals theta. This is where we start, and this is where we're going to end. You can kind of see that just in the picture. We're going in a circle counterclockwise, and we're interested in this area right here. And so the equation that we're going to have is going to be the area is going to be the integral from alpha to beta. What we're going to have is 1/2 r squared d theta. So this is our first big equation for today. Just go ahead and jot that one down. And we're going to look at some examples of how to use this. But again, this is kind of just a basic idea of what a polar function is, the inputs and the outputs, some examples, and now our first equation. So we're going to go ahead and start by looking at an example. So that example is going to be as follows. So we're going to find the area enclosed area Now, of course, I have to give you some polar functions. So we're going to say of r equals to 1 plus cosine of 2 theta. Okay. Let's say for just a moment you're not quite sure what this looks like. What we can do is take a couple values of theta, typically between 0 and 2 pi, and see what we get. So what we're going to do is we're going to say here's our angle, and then we're going to have an output of the radius. And what we'll do is we're going to update kind of this graph right here as we do this. So what we have is, let's say we take 0, pi over 2, pi, 3 pi over 2, and then all the way back to 2 pi. And so essentially what I'm doing, all I'm doing is plugging in these values of theta into my function r. And then what I see is when I plug in 0, I get 1 plus cosine of 0. 1 plus 1 gives me 2. And then all we're going to do is just get different output values. So when I plug in pi over 2, I'm going to get 1 plus cosine of pi, which is negative 1. So 1 minus 1 is 0. And then I'll kind of go ahead and fill in the rest of this. We're going to get 2. When I plug in 3 pi over 2, right here what I'm going to get is 1 plus cosine of 2 times 3 pi over 2, which is 1 plus cosine 3 pi, which is going to be 0. You kind of see what's going on here. And so let's go ahead and graph this just to kind of see what's going on. And so being at an angle of 0 means that I'm currently pointing along the positive x-axis in that direction. And so basically what we have to do is start right here at the pole and then go to the right however many units, in this case 2. That's what we're going to start. So 1, 2. Okay? And then we know that at pi over 2, our direction is going to be up, because that's the angle that we get, measuring counterclockwise to the positive x-axis. But in this case, my radius is going to be 0. So what you can do is plot more points between 0 and pi over 2, put in different values, and what you'll get is something like this. And continuing on, what we get when we plug in pi is we get back to 2. And so we get all the way back to here. And I could just be making this up that this is what it looks like, so go ahead and try different values. Try this for yourself to see what this really is. But essentially what you're going to get is something like this infinity looking sign. And so what we're interested in is the area that's enclosed. Okay? And so what we notice is something that we can use to our advantage in a lot of these problems. Let me make this a little bit smaller. So the area enclosed, let me just draw that in red. What we're going to get is all of this right here. Everything that's on the inside. But what we can notice is that we have some symmetry here along the vertical line x equals 0, or the y-axis. And so what we can do is, actually we also have horizontal symmetry. So what we can do is find the area at the top half area. So what I mean by that is, let's find this area right here in black. Shade it in a little bit more. And then multiply that by 2 to get the entire area. So let's go ahead and look at this. So basically, area is going to be 2 times, right? And 2 times because I'm only taking half of my shape here. So I'm going to be integrating. Now I have to think about what my balance is going to be. So at the beginning, I'm at 0. And then when I'm at this point right here, we have to think about what angle landed us there. And of course, it's going to be pi because we're going in the negative x direction. And then our equation is going to be 1/2 r squared d theta. So the 2 and the 1/2 are going to multiply to 1, so we're not going to write that. We're going to get 0 to pi. And then, it's never just going to be r squared. What we have to do is we have to plug in the function of r. So that is, instead of having r squared, we're going to have 1 plus cosine of 2 theta, all squared. So that's going to be what we're going to integrate. We'll go ahead and do this one. So I'm going to scroll down just a little bit, just to give us some room. And so what we're going to get, I'm going to bring this over here. So we're going to get the integral from 0 to pi. Let's see, of 1 plus 2 times cosine of 2 theta plus cosine squared of 2 theta. Most of the terms here we can integrate no problem, but this last one's going to be a little bit of a problem. So what we're going to do is use the power of reducing trig identity. So we're going to get 1 plus 2 cosine 2 theta plus, and now what we're going to do is we're going to have 1 plus cosine of something over 2. And so typically, if this right here, if the argument were a theta, then this right here on the inside would be 2 theta. So since it's already 2 theta, we have to double it to get 4 theta. So continuing on, what we get is, let's see, one moment. Oops, sorry about that. Don't know what's going on here, having technical difficulties. Okay, that's better. Let's see, maybe not. Okay, what is going on here? Okay, sorry about that. So what we're going to have is the integral from 0 to pi of 1 plus 2 cosine 2 theta plus 1/2 plus 1/2 cosine of 4 theta d theta. Okay, almost there. If you want to skip ahead, I understand this is kind of just some tedious algebra that we're doing. So we're going to get 3/2 plus 2 cosine 2 theta plus 1/2 of cosine 4 theta, and all theta. Okay, let's see if we can figure this out. So we're going to get is 3/2 of theta plus sine of 2 theta. Let's see if that's right. So, yep. And then plus, what we're going to get is 2 sine, no, that's all right. 1/8 sine of 4 theta from 0 to pi. Okay, and so what we're going to get, so every time we plug in a 0 here, each of these terms is just going to give us a 0. So we're not going to worry about that. But what we get is 3/2 pi plus sine of 2 pi plus 1/8 sine of 4 pi. And again, we quickly see that we get some zeros here. These terms are both 0. And what we should get, hopefully this is right, is 3 pi over 2. So 3 pi over 2 is going to be the complete area that we have here in red. Okay, so that's how we kind of find the enclosed area, just when we have one polar function. But oftentimes we have multiple polar functions to consider. And so we're going to be looking at the area that's enclosed between them or inside of one and not the other. And so we're going to go ahead and look at a quick example. First, let's kind of get an equation so we can have some sort of idea what's going on. And so what we have is, let's consider again these two angles that we had of alpha and beta. And again, we're going to have, let's do it in different colors. So we're going to have this blue one here. This is going to be, let's call it R theta, sorry, R naught. And then we're going to have this one in red. I'm going to call it R I. I think I remember what I was doing with the notation. Let me try this again. So what we're going to do is it's going to be R subscript O for outside. That's what it was. It's going to be R I for inside. And so let's say we want to find the area between these two, right? And so just to kind of draw what that is, I want to find this area right here. So we got to think about how we want to do that, and it's not too dissimilar from how we find the area between two rectangular functions. And so what we're going to do is the desired area here is A, which is going to be the integral, same bounds and all, alpha to beta. But we're going to have, same thing, the 1/2, and all we're going to do is, so in our original formula we had r squared, but now we have to subtract two functions, so we'll probably maybe guess it's going to be r outside squared minus r inside squared e beta. This is another formula that we can use. And this is what we're going to use for the next question that we're going to look at. Alrighty, so let's look at yet another example. Okay, so the question is going to be, find the area that is inside our first function, which is going to be r equals 3 plus 2 sine of theta. So we want the area that's inside of this one, but outside of our other function, which is going to be r equals to 2. So this is the example that we're going to work through. And so there's a couple steps that we need to keep in mind when doing this problem. So the first thing is, we're not explicitly given the bounds of integration. So if you look at before, right, we weren't really given them either, and we kind of had to find them ourselves for this question that we did right here. And so the first step is going to be find the bounds of integration, which is going to be the points of intersection. After that, we're just going to plug into our formula, and then we'll be on our way. So, step 1 is going to be, let's see it here, find points of intersection. And again, these will be our bounds of integration. So, we see that when we set these equal to each other, we get 3 plus 2 sine of theta, all equal to 2. So then solving this amounts to subtracting the 3, we get 2 sine of theta equals minus 1. Sine of theta equals minus 1/2. And so then some values that we're going to get need to be theta equals to, what we could do, so we can use 7 pi over 6 and 11 pi over 6. But for this one, what I'm going to do is use, instead of 11 pi over 6, I'm going to use negative pi over 6, which we're allowed to do, and 7 pi over 6. And I kind of broke my own rule of of drawing the picture first. Sorry, I should have done that. So let's kind of see what the area that we're looking for. So what we're going to have, so the easy one is going to be r equals 2. That's going to be just a circle of radius 2, centered at the pole. And then the second one that I'm going to have is going to be a cardioid. Again, it's good to review different types of polar functions, like rose petals, limacons, other things like that. So here, what we're going to have, let's do it in a different color. Let's do red. We're going to draw 3 plus 2 sine of theta. And what we're going to get is something like this. There we go. This is going to be r equals to 3 plus 2 sine of theta. And so let's go back to the statement of the example. This is find the area that is inside r equals 3 plus 2 sine of theta, but outside of r equals 2. R equals 2. And so that area that we're going to be looking for is going to be, well, if we're outside of the circle r equals 2, that means, oops, so sorry. We're going to be somewhere in here, because we're outside of the circle, but we're still inside of the red figure. Not the best shading, but you guys kind of get the picture. And again, we're going to exploit symmetry here, and the fact that this is symmetric about this line right here that I'm drawing. Okay. So we have our picture, we have our points of intersection, and so let's actually look exactly where they touch. So this first point of intersection right here, maybe if I had drawn it a little better, is going to be, yeah, this is a little bit off, but that's okay. This angle right here is going to be the negative pi over 6. This way. Yes, this is fine. The other one right here is going to be 7 pi over 6. And maybe you can see why I used negative pi over 6 instead of 11 pi over 6. Because then we think about starting right here at this point and then move along this direction. So we want to essentially start here because that's when the points first touch. Just kind of a convenient way of thinking about it. And so step 2, let's see here. Step 2 is going to be to find the area. So all we're going to do is plug it into our formula. So plug into formula. And again, we're going to use symmetry. So in particular, what we're going to say is that the area is going to be equal to 2 times. And now we have to think about what our upper bound is going to be. So I'm going to get 1/2 integral. Of course, we're starting right here, negative pi over 6. But since we have symmetry along the vertical line that is the y-axis, we're going to know that that's going to correspond to the angle pi over 2. So we're going to go all the way up to pi over 2. And then we have to think of what our outside function is and our inside function. Because again, that's going to determine what we're going to get for our answer. Okay, so the outside function, of course, is going to be the red one. So it's going to be 3 plus 2 sine of theta. The innermost one is going to be 2. And so what I'm going to get when I set this integral up is going to be, if we look back at what we had before, we have right here r outside squared minus r inside squared. So here we're going to have 3 plus 2 sine of theta squared minus 2 squared. And all that d theta. Of course, the 2 and the 1/2 would essentially cancel. And then you go about solving this integral pretty similar to the last one we had, again using the power reducing formula on sine squared of theta. So we're not going to actually we're not going to go ahead and finish this one up. This is kind of just the setup. The important part here is finding the points of intersection. And then 2, looking to exploit symmetry in the problem. It's always a very important thing in math, in particular when you're looking at these kind of problems, integrating polar functions. Okay, so now we kind of have talked about polar functions and finding enclosed area, or area between two different polar functions. So now I'm going to be looking at a couple of different things, more on the side of derivatives and more linear kind of things. So we're going to talk about the derivative of a polar function and the arc length. So let's start with the derivative. Let me zoom in just a little bit. Let's see. The computer doesn't seem to like me all the time. Okay, let's see what we get. Aha, good. All right. So derivative, or how about we do tangent lines? Let's call it that. Tangent lines to polar functions. Okay, so again, we're going to be using the equation that we've had before, the point slope formula of y minus y naught equal to m times x minus x naught. We're going to be finding the point x naught, y naught, just by plugging in whatever angle we have to be at. And you're going to make more sense in a second when I start drawing. And then m is going to be our derivative. So let's go ahead and find an expression for that. So what we're going to have is our slope. Sorry, not slopped. Slope is, so we're going to have is dy dx is equal to, so we're going to have dr d theta, derivative of r with respect to theta, times sine of theta, and then this plus r cosine of theta, all divided by dr d theta cosine of theta minus r sine of theta. Here's another equation that we're going to use. So go ahead and jot that down. And we're going to look at a particular example. Okay, so example is going to be find the equation. So find the equation of the tangent line. Find the equation of the tangent line. So I have to give you some polar function to r equals 3 plus 8 times sine of theta when theta is equal to pi over 6. And so what do we need? So we need the point, which is going to be r pi over 6. What am I trying to say here? What do we need here? Let's see. Yeah, sorry, that's all that we're going to need. And okay, so you can recall that we had x equal to r cosine of theta and y r sine of theta. And so, in particular in this case, let me get a different color going so that we see a lot of blue. My r that I have is just this function right here. And so what I'm going to have is 3 plus 8 sine of theta, cosine of theta, because I have cosine right here. And then similarly, I'm going to have 3 plus 8 sine theta times sine of theta. So again, all I'm trying to say is we need two things to find the equation of a tangent line. We need the point of tangency and the slope of the tangent line. So what I'm doing now is I'm finding the point in rectangular coordinates, x, y. So we have the x equals r cosine theta from before, if you watched the previous video at the end, and y is equal to r sine of theta. And so now we want to know this point, and the value of this function when theta is equal to pi over 6. So we need to get 3 plus 8 sine pi over 6 times cosine pi over 6. And here, 3 plus 8 sine pi over 6 cosine sine pi over 6. Okay, let's go ahead and write this down here. And so we get that x equal to 3 plus, so sine of pi over 6 is going to be 1/2. 1/2 times 8 is going to be 4. Times cosine of pi over 6. Cosine of pi over 6 is going to be root 3 over 2. So we get 7 times root 3 over 2. Now for y, what we get is the same thing here. So we're going to get 7. We're going to be multiplying it by sine of pi over 6, which is 1/2. So we get 7 over 2. Okay. So we found the first thing that we need. We found our point. So our point of tangency when the line touches the curve. So point of tangency is going to be 7 root 3 over 2, 7 halves. Okay, and we're not done. All we need to do is use this formula that we have here to find the slope, and put it all together, and then we'll be done. Okay, so we get, let's see, sorry. We get that dy dx is equal to, so we have in the equation dr d theta sine theta plus r cosine theta all over dr d theta cosine theta minus r sine of theta. Okay, so we need to calculate dr d theta because we do not currently have that. So let's do that here. So again, r is equal to 3 plus 8 sine of theta. So taking the derivative would just mean that we get 8 times cosine of theta. Okay, so plugging that back into here. So dy dx is going to be dr d theta, which is 8 cosine of theta, times sine of theta, plus, so this r right here is going to be this r, 3 plus 8 sine of theta times cosine of theta, all over. So we have another dr d theta on the bottom, so 8 cosine theta, but it's multiplying in cosine theta, so we have cosine squared of theta, minus 3 plus 8 sine of theta times cosine theta. So this is a lot of work, but nothing too particularly challenging, just kind of a weird equation that we have for the derivative. And so we want this whole entire mess evaluated at, again, theta equals pi over 6. All right, this is what we had in the statement of the question. Okay, so what we're going to get is 8. Cosine of pi over 6 is going to be root 3 over 2. Sine at that point is going to be 1/2 plus, 3 plus 8 sine of theta. So sine of theta there is going to be 1/2. Cosine theta is going to be root 3 over 2. So basically at each point we're either going to have root 3 over 2 or 1/2. We get 8 times root 3 over 2 squared minus 3 plus 8 times 1/2. I forgot the 8 right here. 8 times 1/2 times, I am so sorry. I think I made a mistake here. So on the bottom what we have here is sine theta. Yeah. Okay. So I seem to have made a few mistakes in here. Try it for yourself when you're doing this. It's always better in the first place, just to make sure this is all making sense. I make mistakes all the time, as you can see. Anyway, so right here at the end, and the denominator at the far right, we're going to get this to be 1/2. And so what we're going to get, just to make this a little bigger, actually let's do this, so we're going to get 8 divided by 4, so we get 2 root 3 plus, and then I'm going to get 3 root 3 over 2. And what I should do here is right here, I have 3 plus 4, so I get 7 root 3 over 2 over 8 times 3 over 4 minus 7 halves. So I get 2 root 3 plus 7 root 3 over 2 over, and I'm going to get, let's see, so it's going to be 6 minus 7 over 2, and then yada yada yada, keep going, let's see what we get. So I'm going to get 4 root 3 plus 7 root 3, just to bring this all over 2, over, so this is going to be 12 minus 7, so 5 over 2. So I'm going to multiply it by 2 over 5. We're almost done. Hopefully this is right. So here on the top we have, let's see, we have 10 groups of root 3. Actually, this 2 is just going to cancel here. I'm going to have 10 root 3 over 5, which is going to be 2 square roots of 3. Okay, a lot of algebra here, but again, we have our point of tangent z, first piece of information we need, and we have our derivative. Evaluate at the point. So we conclude by saying that the tangent line, so the equation of the tangent line, line 2r equals 3 plus 8 sine of theta at theta equals to pi over 6 is y minus, so our point was, let's see, somewhere up here, 7 root 3 over 2 and then 7 over 2. So we have x minus 7 root 3 over 2. Sorry, this is kind of hard to follow. I know this is a lot. It's just a lot of, just a little algebra. And then we get 2 root 3 right here. And I'm just going to leave it like that. Okay. So that's how you can use derivative to find the equation of the tangent line of a polar function. So we're going to finish off by looking at the arc length. And this is going to be the last thing we do before we go into vector value functions. Hang tight for just a couple more moments. And so the arc length is the next one to look at. Polar functions. And so the equation we're going to use, so typically we need to know arc length with L. And so L is going to be the integral from alpha to beta. These are my bounds in terms of the angles theta of square root r squared plus dr d theta squared d theta. Alright, so this is the equation we're going to use. You can go away, blah, blah, blah. Okay. So what we're going to get is, well, let's look at an example first. So example, so we're going to find the arc length for r equals to negative 4 sine of theta, where theta is between 0 and pi. Okay, very good. So, let's just go ahead and plug this in. Nothing too difficult here. So L is going to be, my bounds are given to us, 0 to pi. So r squared is going to be 16 sine squared of theta plus, so my derivative here, d theta, is going to be negative 4 cosine of theta. So when I square that, I'm going to get 16 cosine squared of theta. You can probably already see where this is going. What I'm going to get is integral from 0 to pi. Factor out a 16 from both of these. And I get the famous sine squared of theta plus cosine squared of theta, which you should know by now is equal to 1. And so we just get 0 to pi square root of 16 theta. So this is going to be 4 theta, 0 to pi. So we end up with 4 pi. So a lot quicker than the last question. Nothing too terrible there, but again, it's good to know the formulas. And if you've been following along in class, taking notes, you should know the arc length for a rectangular function, y equals f of x, or parametrically defined one. And so this equation looks very similar to those ones. So nothing too crazy. So again, this is, I guess, if you wanted to circle it, box it, or whatever, this is another important equation that we're going to be using for polar functions. Okay, very good. So that about wraps it up for polar functions. Let's go ahead and talk about something that I at least find a little bit more interesting. That's going to be vector value functions. We'll talk about that for a good couple of minutes, and then we'll go ahead and wrap it up for this video. And so hopefully by now you know what vectors are. Vectors are just quantities that have direction and magnitude. There's more to it than that, but just from some basic sort of just description standpoint, that's what we can say about them. And so I like to talk about things with kind of their counterpart. And so let's talk about what scalar functions are first, and then we'll talk about vector value functions next to them. So we do have scalar functions. And then here we're going to write down stuff for vector value functions. Okay, so a scalar function is going to be something where you have any number of inputs, but just one output. And so we have maybe n inputs, and it's just some number, some natural number 1, 2, 3, 4, 5, however many. And we're going to have one output. So some examples of these would be something like let's use f of x. F of x equals x squared plus 2. We'll soon start talking about functions of multiple variables, or multivariable functions. Sorry, just eluded me for a second. Now we'll get something like f of xy. It's going to be x squared minus y squared. So here you have two inputs, but the output is just some number, and it's going to be x squared minus y squared. We're going to denote this with z. The important part is that we have only one output for scalar functions. And so for vector value functions, what we're going to get is something a little bit different. You can have as many inputs as you want, but our output is going to be a vector. So here our output is just one thing, it's just a number. Here we're going to have, and I suppose for now what we're going to say is let's just have one input. But this is not necessarily the case for vector value functions. You can have as many, but for the purposes of this class, for 2419, we're just going to be looking at one input. And our output is going to be not a number, but a vector. So output is a vector. So the thing that we're getting out is completely different here. And so let's look at some examples. Let's say we have some function. We're going to call it r of t. And again, I'm using this hat notation because we're talking about a vector value function. And I'm going to get 2t, t cubed, e to the 2t. And so here I plug in some value of t. And what I get is I get some value here, here, and here. And that's going to give me some number. In this case, it's going to give me a vector in R3 at the end of that process. So these are what we call the component functions, because they're functions in each of the components of this vector. And so the way we write vector valued functions in general, so we get a thicker marker here. Alright. So what we're going to have is in general, we're going to write r of t. So you can think of this as your position vector if you're particularly physics oriented. This is going to be f of t, g of t, and h of t. So each of these component functions has t as its input. Okay, so we can do a lot of fun things because now when we start looking at vector value functions, we start looking more into 3D space, which I find very fun. And so let's do a quick question, and then we'll talk about domain, and then we'll end there for today. And so the question is going to be sketch r of t equals 4 sine of ti plus 4 cosine of tj plus tk. And so if this kind of confuses you, the ij and k part, it's just telling you where to put each of the components in your vector. So if it's multiplying I, then that component function is going to go in the first spot. So we basically have this function, 4 sine of t, 4 cosine of t, t. And kind of like a healthy way to view this relationship, or like what's going on with t, is to view it as time. And so as t increases, we would just say that time is passing. We're viewing this function as time goes on. We want to see what happens to it. And so let's look at what happens right here in the x and the y components. And so what we see, here's y, here's x. 4 sine of t, 4 cosine of t is going to get me a circle of radius 4. So this is what I'm trying to say is this is some standard parameterization of a circle. In particular, when I do this, I'm going to be going, I believe at least, counterclockwise. Okay, so let's just imagine we cover up this t right here just for a second. And just look at the first two. So as time goes on, all I'm doing is going around a circle counterclockwise. In particular, a circle of radius 4 centered at the origin. And so as t increases, z is going to increase linearly with it. Because this function right here, right, is just like h of t equals t. And so as t increases, as t increases, h of t increases. Something like that. And I guess we can go negative, doesn't really matter. And so all the while this circular motion is happening, what's happening in the z direction is we're just going straight up. And so let's combine these two pictures right here and right here to get what's really happening. This mark is very nice. Okay. And what we're going to get, so here's x, here's y, here's z. So to kind of shift your perspective, so here in the xy plane counterclockwise is this, here it's going to be like this, right? But what's going to happen is while I'm going around counterclockwise in the xy plane, my z is increasing. So I get this helix. And so that's going to be what my vector value function is going to look like. So pretty cool stuff. That's really it for this question. We'll look at one more, and then we'll call it. Okay. So what we're going to do is, let's get that big marker going again. I like that one. Okay. A little smaller. So we're going to, last question, determine the domain. Determine the domain of the vector value function r of t equals to cosine of t, natural log of 4 minus t, and square root of t plus 1. Okay. And so the way we do this is we look at the domain of each component function and then take their intersection to see where they all overlap. And so let's look at cosine of t first. Let's see where my color. There we go. So cosine of t, well, this function is defined everywhere. There's no value t that can plug in and not get an output value. Okay. Natural log of 4 minus t. Well, I know that when I take the natural log of something, that the inside cannot be negative. So that's kind of what we would say, like in English terms, like in words, right? What that means in equations is that, well, let's see. So 4 minus t this has to be positive, this has to be greater than 0. So that means that 4 has to be greater than t, or the way I like to read it, t less than 4. Okay, and we look at the last one, square root of t plus 1. Now we know we can't take the square root of a negative number. And so what that means in inequalities is t plus 1 has to be at least 0, greater than or equal to 0. So t has to be greater than or equal to negative 1. So we're only going to have problems here when we look at natural log, square root, or when one of our components is some fraction, and when we can't divide by 0. And so let's look at what we have. What I like to do is draw this number line. And so I have two conditions. T has to be less than 4 and greater than or equal to 1. For something simple like this, you might not have to draw this, but I think it's good practice. Negative 1, 4. And so t has to be at least this, but t can be no greater than positive 4. And so we see that intersection is when we have both the black and the red. And so it's going to be right here, including negative 1, but excluding 4. So we conclude that our domain for r of t is negative 1 to 4. Open parentheses. Thank you for watching. I hope you have had a good time learning. Have a good rest of your day.